Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, find x sum of all k long subarrays 2, the sequel to yesterday's problem, which I said actually doesn't have a more optimal solution than the brute force one, and it turned out that that was a lie. So let's get into it, and I guess before I get into this problem, I'm going to say that the algorithm from this problem is very similar to another famous hard problem that you might have solved before. It is a part of the Leetcode 150 and 250 list, so if you've gone through that, you've definitely seen it before. It is find median from data stream. If you haven't gone through that list or you haven't seen this problem before, I would encourage you to do so. I think this version of the problem is honestly a little bit easier. And specifically, I think it's the 2 heaps solution that is the one that's going to be similar to today's problem. I won't go through much of the description because the idea is the exact same as the easy version of this problem. The only difference is that I think the input size could be much, much bigger. So the brute force solution, which I believe was something like n times k log k, or at least something like that. Today's solution, I think, is going to be a lot closer to just n log n, so eliminating that k term, which in the worst case, it could be up to the size of the input array, so that is pretty significant. So let me kind of revisit the idea of tackling this problem with the sliding window. So remember that the solution to this example, it's going to be something like this. So let's say k is equal to 6. That's going to be the size of the window. X is equal to 2, so that's the 2 most frequent numbers that we want from our window. And if there's a tie, we want to use the value of the numbers as the tiebreaker. So largest is going to be preferred. So in the first window, we have something like this. If we were to get the frequency of each of these, which we're almost definitely going to do if we want to identify those numbers, it's going to look something like this. 2 is going to map to the count 2. 1 is going to map to a frequency of 2, and 3 and 4 are going to map to a frequency of 1 each. I guess to put them in sorted order, I'll do this and this. So that word that I just mentioned, sorted order, that's going to be the key to this problem. But it's not going to be trivial on how to do it. But obviously, we're going to need some kind of sorting mechanism, because if we indeed want to perform the sliding window, we have to make it so that when we shift this window, once we have the solution to this window, and then we go to the next one, we want to be able to just remove this and add this. And we want to do it without having to take all of these numbers and then resort them, because that's going to be the n log n operation. And we know we're going to have to do that proportionally n minus k times. Okay, so how do we do it? Well, if we can't run the sorting algorithm, I think at the very least, your first thing to try would be some kind of sorted data structure, right? So the most common one usually that works is a heap, a min heap or a max heap. Let's try to see what happens if we try to solve this problem using that. Is it going to make things more efficient? Is it even going to be possible? Well, let's say we are maintaining this mapping because we do want to know the count of each value. That's always going to be important. But we also want to be able to order these. So if we were to throw them into a heap, how would we want to order them in the heap? Well, the first thing we want to use is the frequency. That's going to be the key. And the second thing is going to be the number itself. So it's similar to how we ran the sorting algorithm yesterday. We're still using this as the sorting key, so this is going to be used as the key for the heap. Okay, and let's say we had all of these pairs in the heap, like each of these is a pair, and each of those is inside of the heap. Well, it seems possible because assuming it's a max heap, we pop the most frequent one. If there's a tiebreaker, it'll use the number automatically. That's great. So we pop this guy. Okay, that's fine. We do 2 times 2. That's like the sum of these. Okay, and then we keep going. We want to get x of them. So next we get 1. 1 times 2, that gives us these 2 elements. And then we're done. Okay, well, we updated the heap and we removed these. We don't necessarily want to remove these from our window. So let's go ahead and just add them back to the heap. Okay, that's fine. So far, so good. But now you're going to see the problem with this. We want to shift. We want to get rid of this one, and now we want to add the 2. How do we do it? Well, we can't remove an individual, like a specific key from the heap. We can't choose what we remove from the heap. Typically with heaps, we can only remove the maximum. or the minimum, depending on the heap. And that's usually a log n operation. I mean, theoretically, we could go through the heap. We could search the heap and identify one and say, okay, this pair, 1, 2, now it should be a different pair. It should be 1, 1. That's possible, but how do you think that's going to happen with a heap? We're going to have to potentially iterate over the entire heap. The heap is of the size of the window. So it's really not going to be any better than the brute force solution, right? Like every step, every time we shift the window, we're just going to have to scan through the entire window again. Doesn't really help us. So I could be wrong, but I don't think there is a super efficient solution with a heap. I mean, maybe there is. It's just possibly really convoluted. If somebody has that solution, feel free to comment it. But I think the better choice for data structure is going to be the cousin of the binary heap, which is it is the binary search tree. And you might not have thought of this data structure. I pretty much never think of it in terms of using like the library, because it's very rare that it actually comes up. Typically, we can just get away with using a heap, but this is one of the cases where using a binary search tree is actually going to be important. And I'm going to be using in Python something called the sorted list, which, don't let it confuse you, it's not just a sorted list. It provides log n insert, remove, and search operations. So that's going to be the key to solving this problem, not using the heap. Okay, so how is it going to work? Well, I'm not going to like draw out the entire like sorted list, but let's assume we have that as a data structure, a sorted list or a binary search tree, whatever your language provides. Just make sure it has log n, insert, search, and remove. What we're going to do is for this window, initially, we might think that one instance of this is going to be enough. And as I kind of hinted at the beginning, that's not going to be the case. And I'll try to show you why. So as we're iterating from the beginning, we'll have one, and then we'll have another one, and then we'll pretty much have these counts. So the first thing, like 1, 2 might be added to this data structure. Next, 2, 2 is going to be added, and then 3 is going to be added. But here's where it comes in. So if we had this sorted list, and we just keep adding these, assuming we're storing them in sorted order, and I'm not always going to draw it that way, but just assume that they are in sorted order. Assuming that they are, we could kind of just get like a prefix or a suffix of this. So if they're in sorted order, that list might look something like this. I think 1, 3 is the smallest. Next we have 1, 4. Next we have 2, 1. And lastly, we have 2, 2. Remember, the first is the frequency. The second is the number. So these are in sorted order. We know that there's not going to be any duplicates because we're storing the frequency with the number. So we're not going to have that same number show up multiple times in here. So what we can do now is just get the suffix, the last X elements, and just take them like this, iterate over them, and then compute the product of these two, and then add that up. And that does work. I think the time complexity of that is going to look something like, I guess before getting into the time complexity, let me show you what would happen with the shift, because that's kind of the important part. So now we're here. Next, we're going to shift. We're going to remove this 1, and we're going to add this 2. How would we handle it? Well, we're looking for 1, and we know what the count of it is because we have this hash map. So we know we're looking for the tuple that looks like this, the tuple 2, 1, count of 2, value of 1. So we can find it in this sorted data structure, and we can do that in log n time. And we can update the count of it now. Before we update the count, let's actually remove this because we're probably going to need to add it back in sorted order. So let's remove that, update the count. Now it's going to be a 1, 1. And now let's add it back in. It's probably going to go at the beginning of this. So that was perfectly fine. Well, we can do the same thing with this 2. Now we can search for the value 2, and we know 2 has a count of 2. So we're looking for this tuple. We find the tuple. We increment the count. This is the count by 1. So it's going to be 3, and then we would add it back to the sorted data structure. So all of that's fine. We're doing a log in operation on each iteration. But remember that also we're going to have to take the suffix of this array, the last X elements. So we're also doing an operation times X, and we're going to do that potentially n times. That's how many times we'll have to iterate in the worst case. More precisely, I think it would be n minus k. So it's not bad, but we can actually do better. We can actually eliminate this x term by adding a second sorted list. And that's actually not a small improvement either, because x could be, I think, roughly the same size as k in the worst case. So in that case, like, this would be the exact same time complexity as the brute force solution. So this optimization I'm going to show you, introducing two lists, is going to be really, really helpful. So remember that the bottleneck is this x term. The bottleneck is taking the suffix of the array, taking those top x frequent elements and then computing the sum. So the way to get around that would probably be just to maintain the sum. Let's call it our current sum. So just have a variable and always know what it is. Always know what those top k or top x elements are. And you probably see where I'm going with this, but still, to kind of show you the logic behind that. But I guess, why can't we just use one sorted list? I'm actually not 100% convinced that we can't. Like, it might be theoretically possible, but you'll see that naturally when you try to do it with just one sorted list, that it becomes kind of intuitive that you'd want to split it up into two, because we see that we want to maintain like that suffix, like the top x of them. But we also know that things are going to be shifting around. Like, this boundary is going to be important. And I know I kind of drew this array awkwardly, but imagine like they're all stacked like this, like there's 4 of them, and we have like a boundary over here. We just want these. Well, if we have some elements over here and some elements over here, possibly we're going to take this one and decrement it. Maybe it's going to get swapped with this guy, and then this guy's going to come over here. Or maybe it's going to get pushed over here, and then still, like, these are going to get shifted over to the right. You notice that it's all about the boundary, that this guy, if something is removed from this side, it's going to be this one that takes its place. And similarly, if something is removed from this side, this one is going to take its place. So it's all about the boundary, and that's why something like a heap or a sorted set is going to be good for this part of the problem. But remember, we talked about why a heap is not going to work, because removing and adding like arbitrary values from a heap isn't really supported, because we know that as we're kind of shifting our window, we might not just be updating the boundary values, we might end up updating this one, and now all of a sudden this guy is shifted all the way over there, and then this guy gets shifted there. So this is the general algorithm. We're going to have two sorted sets. One I'm going to call the top one, the top x elements, and the other one, let's just call it remaining, or whatever is left over. If we have enough elements, we really want to just push them into the top heap, or the top sorted list. But maybe this one reaches capacity, and then we start adding other elements over there. Well, specifically, let's assume we're always just going to add those elements to the top heap, but if the top heap gets too big, well, then we're going to take the smallest value from the top, or not the heap, the sorted list, sorry. We're going to take the smallest one and then add it to remaining. I think that's pretty similar to how the find median problem works that I mentioned at the beginning of this video. So I'll try to do a dry run, but it's going to get kind of complicated. So I'll try to keep it like high level. So let's say initially we got these two values, we add them to the top sorted list, then we add 2, so these 2 are in the top sorted list, and then we want to add 1 to the top sorted list as well. Well, it's going to look like this. The frequency is going to go first, and then we see, okay, top sorted list is the length is bigger than x. So what do? We take the smallest one. I'll show you how to do that in the code. We're going to take the smallest one and then remove it, and we're going to add it to remaining. Next up, we're going to do the same thing with 4, and so now we have a single window that is of size k. We're going to take the sum of the top elements, and the way we're going to do that is by tracking a variable current sum. Every time we add to the top sorted list, we're going to add to that. Every time we remove from here, we're going to decrement from that. And now, finally, the shift case is when we're going to do this. We're going to now, instead of just adding 2 to the top heap, or the top sorted list, we're going to remove this one. And we actually don't know where 1 is. We don't necessarily know if it's in this sorted list or if it's in the other one. So we can just check. We can do a lookup on this data structure in log n time. That was the whole point of using this over a heap. And we can check, is it in here? If it's not, we'll check this in log time. And in this case, it was here. So we're going to end up taking the tuple to 1 and decrementing the frequency down to 1. And that's where things get interesting. Because now, for this element that we updated, we need to potentially rebalance these two sorted lists, because maybe this one doesn't belong here anymore. And that could have happened in multiple ways. One way would be the case that we're looking at now, where the frequency now is too small because we have other elements over here, such as this 1,4, which has the same frequency, but a bigger value. So how are we going to do that comparison? Well, the easiest thing to do is just compare this guy, wherever it is. It could have been here or it could have been over here, and compare it with the boundary value, meaning the biggest value from the remaining sorted list. And if it's smaller, then we will move this one into remain, and we'll take this one and put it into top. So that was one case where we have to do the comparison. The other case is where maybe this one had a frequency of 1, and now we took the frequency all the way down to 0. So actually, this one isn't going to be moved anywhere. It's just gone now. So we have an empty hole here. The length of this guy is less than x now, and we do have some extra values in the remaining sorted list. So take, again, the biggest one and add it here. So those are the main cases we have to worry about. And as you can kind of see, we're just doing a bunch of like sorted log n operations. And I think it's actually log k, because theoretically the size of this should never be bigger than the sliding window. So I believe the time complexity is going to be n log k. If you want to get more precise, I think it's n minus k log n, something like that. Anyways, I don't think you really need to get too precise usually. But anyways, let's code it up now. I would say in this problem, the hardest thing is the bookkeeping. Like, there's going to be a lot of code. Most of it isn't crazy complicated, so I'll try to walk you through it. I'm going to start with just a bunch of variables, and let me just declare them first. So like I said, we're going to have a couple sorted lists where the tuple is going to be frequency and number. We're going to have top and remain. We're also going to have a hash map, which is called frequency, mapping each number to its frequency. And that's going to be within the current sliding window. And we're also going to have the result array, and we're also going to have the current sum, which we're going to keep track of. That's going to be what gets this to be an efficient solution. And now let me show you how they're going to be used. And before I do that, let me just say we're going to have a couple helper variables. One is going to be add a number, and one is going to be remove a number. When I say add and remove, it's not specifically to just one of these, it's to this entire thing. Like we're keeping track of this data structure, meaning like the top and the remaining elements. When I add this number, I'm basically updating both of these and then potentially doing that balance, like that rebalancing between them. It's going to make more sense once I actually write it out. But for now, let's assume that they work. And if you assume that these work, the problem becomes trivial, because this is what I'm going to do. First, I'm going to go through the first k values. You could do it another way, but I think this way is fine. And I'm going to add each of those values. So nums of I is going to be added to our lists. So after I'm done with that, I can assume that all these variables are updated, and we'll except for the result, which let's move down here just to make it more clear. And let's assume the current sum is also updated, because if we can update the lists, we can definitely update that as well. Well, if we do that, then we know that we can add to the result the current sum of the current window. And then after that, we will update the window accordingly like this for I in range, starting at k now, going up until the end of the array. We're going to remove the value all the way at the left, which is index I minus k. And we're going to add the current value, nums of I. And then whatever the current sum ends up being, we're going to append that to the result. And then we can just return the result. So now the fun part, actually implementing these functions. I'd highly recommend you try doing it yourself, but I'll show you that they're both going to be very, very similar, and we can actually combine both of them. But first, let's start with adding. So we're going to need to update the current sum, so I'm going to declare that as non-local here. And if you're confused by like some of this Python stuff, like how I'm doing these functions, just treat these as if they were like member variables of self, because we're basically going to treat them as if they're accessible in here, which they are. And now we're taking this number and we're adding it. So obviously we want to increase the frequency of it by 1. And there's another case. We want to take this number and add it to, well, one of these lists for sure. The one I favor is going to be top. You could add it to the other one if you wanted to. Your code is just going to be kind of the opposite of mine, but I'm always going to add it to the top list, even if the top list is already at capacity. So I'm going to do this, top.add frequency of the number, and then the number itself. Now, do you see a potential problem with that? What if this number was already added to the top list, or maybe it was in the other list, the remaining list? Well, we should probably remove it first. But how do we know if it's even in either of those lists? Well, we could check by just checking either of them. But one way to check is also to just use the hash map. So like this, if num is in frequency, well, okay, now we know it's in definitely one or the other. And before we increase the frequency and then add that, let's use the original frequency and number and set that to what the previous tuple is. Because we know for sure this number exists. We know this is its frequency. So this tuple should definitely exist in one of these lists. And we can check which one. If previous is in top, or else that means it's in the other one. It has to be in one of them. If it's in the top one, well, definitely we want to remove it for now. But if we remove it from top, in order to do the bookkeeping of tracking the current sum, and the current sum is tracking the top elements, we should decrement the current sum. And we're going to decrement it by the, I believe, the product. So it's going to be these two values like multiplied. So just like that. In the else case, we are also going to remove it from remain like this. And we don't have to update the current sum in that case. And honestly, I think we don't even need this variable previous. Just to make it more clear, let me just actually do this and this. Maybe you prefer the other way, but I think this is fine. Okay, now that we have that, there's only one last thing to do here. It's to do the balancing. And I'm actually going to put that in a separate function because we're going to need to do it in the remove function as well. That's just kind of a spoiler. If you were to implement this code, you'd probably realize the exact same thing, but I'll just mention that to you from the beginning. So I'm going to have a function called balance. So this function balance isn't going to take any parameters. It's going to use the current sum potentially, but most importantly, it's going to be baked with some assumptions. And that assumption is this: we're always going to try to keep the two lists balanced as much as we can. But if they do go out of balance, they can only go out of balance by one element, because top should never exceed the size of X. But if it does, like if it's equal to the size of X and now we just add one more element, well, it has one extra element. It's never going to have two extra elements because we're going to always call balance right after we do that. So if you know that assumption, this function becomes pretty trivial because you can do this. If the length of top is greater than X, well, then we can pop from top, and we actually want to pop the smallest element. So we don't just do pop, we do, we pass in 0 as the index. So that'll give us the smallest. Then we'll get two values, the frequency and the number. And then this is going to be added to remain like this. And let's also update the current sum, which is now going to be decremented by f times n. And that reminds me, we probably should have updated the current sum down here too. So in this case, let's increment it by frequency of number times number. So that's one case. The other case, which I guess I'll just fill in now, is going to be when we call balance within the remove function. Because in that case, we might be removing from top. So top might not have enough elements remaining. But let's say that's the case. Length of top is less than X. But there's also some elements remaining in remain. So if that's the case, we're going to pop the element from remain. And in that case, we can just do pop without passing in any parameters, because I think by default, this will pop the max value from remain. That's what we want. So fn, and then we kind of just do the reverse of this. So I'll just copy and paste this real quick, because now we are adding to top, we are incrementing the current sum. And then the last case is going to be the interesting one. So what if we did some logic, we remove some value from top, and now maybe we add another value, kind of like how these two consecutive calls are being made. We remove and then we add, and the two lists become out of balance, not in terms of size, but in terms of values. Like the top one doesn't have all the top values. Well, again, that could only happen by one. It'll be missing one of the top values. And we know exactly where to find that top value. It's going to be in the other list. So we're going to say if top and remain, and the smallest value in top is smaller than the biggest value in remain. We can get that at index -1. If that's the case, then we just need to swap them. So let's do F1, N1 from top, popping the smallest one, and getting the biggest one from remain is going to be like this. And then we're just swapping them. So it's going to be that. And then the current sum calculation is also going to be pretty simple. Just going to be this product being added, this product being subtracted. It's going to look like that. So now we're almost done, and it's kind of a lot of repetitive code, but now we're just going to finish up the remain function down here, or sorry, the remove function. And I'm just going to kind of copy and paste the code up above because it's going to be almost the exact same. Once again, we're going to check, is this number already in either of the two lists? If it is, let's remove it and update the current sum accordingly, because we're going to take that and we're going to, instead of incrementing the frequency, we're going to decrement the frequency, and then we're going to add it back to top. And instead of incrementing the sum, we're going to decrement. Or actually, no, we are going to increment this, because what we did is we decremented here, then we updated the frequency, added it back, so now we can add the new value back, and then also rebalance. This is just missing one very important thing, which is, what if the frequency becomes 0? I mean, I guess it wouldn't matter in terms of these calculations. I mean, this calculation would become 0, but it does matter in terms of the size of this, because we don't want to count zeros when we're taking the length of the top list here and here. We don't want to count those guys. So let's do something here. Let's say if frequency of number is equal to 0, let's delete that element from the hash map. Otherwise, let's go ahead and do these two operations. Let's add it back to the top list and then update the sum accordingly. We're always going to balance in both cases, because if we never added that element back to top, we definitely will need to rebalance in that case. So this is pretty much the entire code. You can see it's about 70 lines. I can show you a few ways to shorten it, and I guess I will, but let me run this first. And you can see here, does work. It's very efficient, and I'm going to go pretty quick when I condense this code. One is kind of not obvious, but it's that instead of adding to top, if you actually always add to the remain heap or the remain sorted list, things work out better. And actually, before I even do that, I'm going to get rid of one of these functions, and I'm going to, instead of having add and remove, I'm going to have one called update. It's going to pass in a delta, and that's going to be either +1 or -1, and then that delta is going to be used over here. And I'm going to change this to a plus. And I'm going to, like I said, instead of always adding it to the top, I'm always going to add it to remain. Then we don't need to update the current sum here. And more importantly, then we can update our balance function actually by getting rid of one of these cases. And I think it's going to be this one, because if we always add to remain, we don't have to assume that top is ever going to be bigger. And this case might still possibly happen. And this case might still possibly happen, but the other ones won't. And lastly, let's get rid of add and remove and change these to update. So here we'll have a +1. Here we'll have a -1. And here we'll have a +1. So we shortened it to about 48 lines of code, and there's still a decent amount of spacing. So let's try to fit most of it on one screen. So there's that and that. Let's run it. And you can see it also works. I'm not gonna lie, that one was pretty annoying to record, but if you found it helpful, check out Leetcode.io for a lot more. I'll see you guys soon.